Okay, so today, we're going to start talking about uh, quadratic polynomials and factorization, like mostly factorization, in fact. That is one of like the most important topics of the course. Like factorization is like really useful, and it appears a lot of in tons of different places. Um, It is in a sense like the reverse process of multiplication, and I'll explain what I mean by that. So it's kind of like reverse multiplication. But I would say that between this week and the next is when we will cover probably like the most important things like that we have to discuss in the course. So first, let me start by kind of like reminding you of like this E property of multiplication, which is like distributive property, which we have used before, but it is important to kind of like write it down again. So we have the distributive property. Uh, which sometimes is referred to as like foiling, like. But what it says is that if you have something like this, I'll write it in this way because like that will be the most useful way to think about it for today. When you have like a product of two sums of quantities of numbers, then what the distributive property says is that well, 2 times 2 equals 4, so you'll get 4 things here. And basically what you get is like all the possible products that you could do between these 4 numbers. So you can do A times C, you can do A times C. Okay. You could also do B times C, and you could do also B times D. Okay. So those are the 4 products that you can make between the individual terms. And then the property, like because all of this was with addition, is that you end up adding all of these quantities. Now, where does that come from? And I may have mentioned this before, but why does this work? Let's see, just checking I'm recording. So why is this correct? Why? I mean, so one way to think about it, which is convenient, at least just to see where the property comes from, then you can just forget this picture. But like it comes from like areas basically. So you can just imagine that you have a rectangle. Um, I have a rectangle, and I'll just say that one side has lengths A and B. Okay. And the other side has lengths C and D. These colors do not match, it's just I don't have enough colors. But so the total length of the like rectangle, like sorry, each of the sides, like I'm kind of like the length, think about it as being made out of 2 pieces. Okay, so the area of like this big rectangle, so if this rectangle has area, well, what is the area of a rectangle? It's like base times height. So the base is just the length of the segment, which is A plus B, right? And the height is the length of this side. which is C plus D. Okay. But but these, if you now think about it, you can break this rectangle into four pieces. Okay, and the area must be the same. So what are like the individual like mini rectangles that you have here? Well, like one rectangle, this one has area A times C. And the other one, I'm gonna try to use the color, I'll use the same colors here. Like this one has area A times C. This one has area, this other one has area B times C. This other one has area A times Z. And the last one has area B times D. Okay. That makes sense. And if you kind of compare like these areas, like these let's call it area one. Area one is right here, right? Area two, where is AD? AD is right here. Area three is this one, the third rectangle is right here, and the fourth rectangle is okay. That kind of like in the way I wrote it. So you see, I'm just like the distributive property, basically just saying that when you have a big rectangle, you can break it into four pieces, and the area of the four pieces have to be added up. If you were to add the area of the four smaller pieces, that just gives you back the area of the original rectangle. Now, does that make sense? That makes sense. Now, why is this useful? In practice, so I'll kind of write it a bit more abstractly, but and then I'll kind of give you some more examples. But in practice, the way that you do use this is like usually the way you think about it is not that you start with the product of two numbers kind of like expressed out very nicely in parentheses. Rather, you kind of like in practice start with like all this bunch of terms and you kind of want to regroup them in a way that looks like as a product of two sums. So in practice, we the way we want to use this property is not going from the left side to the right side, but kind of like going from the right side to the left side. So in practice, this is how it would look. In practice, you kind of want to kind of combine a bunch of terms into like a product of sums. So in practice, we want to group the individual terms into a product, into something which looks a little bit more simple in a sense, into something that looks more simple. So the way this would work out in practice is that you would be given something like this. Okay, you would be given something like this. So kind of like all the terms being added up together, which kind of looks a little bit more messy. And then you would go and say, okay, the first two terms share the factor A, that's how you would say it. So they have the common term A. Since they have the common term A, you can factor it out, okay? And after you factor it out, what you get left from each of like these summands is C plus D. And the last two terms for like one of the things that they have in common is B, right? And then you can kind of factor it out, and when you factor it out, like the last two summas, what they're left with is C and D. Okay, and so what is this corresponding to? If you look at these two, like, why does this make sense? Like, again, you can think about it in terms of the area. If you look at these two, you're kind of adding the area of the first rectangle with the area of the second rectangle. Okay, that is what the first two terms correspond to, these two areas. And if you see, I'm just saying, like, the area of this rectangle, these two rectangles added together is the same as the area of the rectangle that had, kind of like if you kind of glue them together and just forget that they're two pieces, like you, because it's like a rectangle with base A and side C plus D. So it kind of makes sense if you look at it from the area perspective. And likewise with these two, what is happening with the last two? So the last two is adding the area of the third and fourth rectangles, right? And when you look at it, when you add up those two areas, I mean, that gives you like a slightly bigger rectangle here, which has base B and, the other side is C plus B, which is what you see here. So it actually, it really just like this, which you typically refer to as factorization, is really just like in terms of area, it's just saying that when you had like, these four pieces, you can kind of put two together and then these other two together and the areas have to be the same. Okay, and once you see that, it's making sense by the way, kind of. So once you see that, then you can say, okay, now there's something similar going on here, where I have C plus D, C plus D on this end, okay? And so since that's a common term, I can kind of factor it out. Okay. But then what is each term, what is left after you take this out? You get your end up getting A plus B. Okay, but then it doesn't matter in which order you write a multiplication. Like you can rewrite it if you prefer as A plus B times C plus D, which is essentially what we had started with. So in practice, the way this distributive property is used is not kind of like to take this product and like find this product. Is rather like you have like a bunch of terms and you kind of want to recombine them in a way that give those to you kind of like as a and just to set like just multiplication of two things rather than like a sum of four like different products. Okay, so that is kind of what is called factorization, where like instead of like kind of going in reverse, because if you think about it, going from the left side to the right side, let me put like a diagram here. To go from the left side of the equation to the right side of the equation, when you do some sort of multiplication, which is what I did here, like, I did all these possible products. But if you kind of have all these terms and you want to go backwards, what you're doing is what's referred to as factorization, which is kind of like finding the common terms in your expressions. Now, let me copy the factorization property on the leave it here in the top right corner because I'll be referring to it. So today, like we're just going to do problems like this, but I'm about to do something a bit more concrete now. So, let me show you why this is. What's the point of doing this? Okay. So why do you want to do this? Let's discuss that. So why should we do this? Okay, so up to now, so like Up to this point, we have been solving certain equations. Up to now, we have been solving linear equations, right? We have been solving linear equations, right? So for example, like, if I had given you something like 2x plus 4 equals 0, the way you solve this was like you could add -4 to both sides of the equation. We find x equals -2, right? That kind of we have already become familiarized with that type of problem. But the point of a linear equation is that the coefficient for x is always 1. So it's x to the 1. Like you don't have anything that kind of involves like an x squared or an x cubed or something more complicated. So that the next step, once you kind of master the linear equation, is to move to the quadratic equations. And that's kind of what we will focus this week and the next, because that is like the most important topics of the, I mean, quadratic equations is by far the most important topic of this course. So now what we want to kind of do is kind of like, deal with that slightly harder problem. We want a more complicated problem, a more complicated problem. Um, so, because this is probably something maybe you have seen before, like, let's just say, it's kind of important to understand this. So what is something you could try to do? Like, if you kind of were to take like a similar approach to what I just did here. One thing you could try is like to say, okay, like what I was trying to do here was kind of like isolate the x, right? So you could try to do the same for this type of problem, right? So let me do that. So I'll like subtract a 6 from both sides of the equation, right? So you get end up with x squared plus 5x equals -6, right? And then you end up with like okay, so once you get here, the problem is because like this what makes this like a quadratic equation. You don't have something like just like an equation for x, right? Like, you have x squared plus 5x, because like now the point is that this being a quadratic equation, because like there's a 2 here, you won't have just like a single thing for x, but you could still kind of like think, well, maybe that there's like a common x present in both terms, right? So you could factor it out, which is kind of I have been referring to this process, right? There's like an x here and an x here secretly. And it gives you x plus 5, right? And you get to something like that.
What would you call that, like itself, taking the x out? Boiling?
No, you would say like factoring out an x, for example. Foiling would be more like if you had x times x plus 5, it would be kind of going from this step to the previous one, so it would be going backwards. But yeah, if you have x squared plus 5x, going to this like last thing that I just wrote is what you would call like, in this case, like factoring out an x, because that's like kind of what was like the common thing in both terms. Okay. out, and then once you get here, okay, so here's something you could think about. You could say, well, what is this asking for you to do? This is asking you to find, you know, you're saying, oh, you're trying to find a number x with the property that x times x plus 5 equals -6, right? And so you could be thinking, like, maybe, and this is like going to be wrong, but like I'm just going to kind of show you what you could think. You could think, well, -6, what is -6? So, well, -6, for example, you could say it's like -2 times 3, right? Like that is -6. Also -6. So you could maybe, for example, say, well, maybe this means that, since -6 is -2 times 3, that x should be -2, and maybe x plus 5 equals 3 or something like that. So maybe you could say, does this mean that x equals -2 and x plus 5 equals 3? Okay, but I mean, you quickly see like that this wouldn't work, because if x is okay, no, so actually this one does work. So I take it back. So does work. But what if you had said, someone could have said, oh, but -6 is -3 times 2. I think this one would have been better. Okay, so if I say that, like, because that's also true, right? Like -6 is also -3 times 2. So I say that, and then you compare, and then you are like, well, then just by comparison, you can say, well, what if x is then -3 and x plus 5 is 2? Okay, and this one will still work. Good. Okay, this is getting interesting, right? But is it? Now you are like, okay, is this the only way this could have been done? Because there are other ways to write -6 as a product, right? So you could have said, here's another one you could have said. So I'm just giving you a bunch of ways in which you could write. Okay, so you could also say that -6 is 6 times -1, for example. Okay, so now if you have that x times x plus 5 is 6 times -1, then you could say, well, then x should be 6, right? And x plus 5 should be -1. Okay, and then now this one, definitely this one is wrong. Okay, finally, this one does not work at all, so this one wouldn't have worked, won't work. Well, because if x is already 6, x plus 5 is going to be 11, not -1, right? Or likewise, you could have said, for example, like, and -6 is like -1 times 6, right? That's also true. So it's a bit messy because like this is not what we're going to do, but I'm just trying to show you like some of the one of the things you could have tried. Okay, and then if you have it, then you would say, well, maybe that means that x is -1 and x plus 5 equals 6, right? But again, like if x were -1, then x plus 5 would be giving you 4, not 6. So this one also wouldn't work. So like here was one option which won't work. Here is an option which wouldn't work, and then we did find two options that do work, right? So like when you do this from this perspective, it can be a bit tricky, if you just do it this way, it can be tricky, like how many options to look for, like how do you know when to stop and things like that. So that is why you really don't try to solve the problem this way. Although, like, yes, if you do it by trial and error, it did work for the first two, but it didn't work for the last two. Okay. but it's still like an interest, it does have like a grain of truth because it is close to what we will do. It's just that what we will do is a bit more systematic and not like something that looks a bit too random, okay? But my point is that, when you have an equation like this, like which is quadratic, it's not as obvious, it's not as clear as what we were doing before, right? Where you would just like, solve for x directly. Here, like what I did, it was kind of like to decompose it as a product, and then I wrote 6 as a product, and I kind of like, I got some like partially useful information from there. But my point is that, like, if you kind of try to set it up from this perspective, like it is not as straightforward as before. So like this is not what we're going to try to do. Like what we're trying to do is something that kind of works more in general. So what I'll do is kind of like redo this problem in like more closely to like the method that we'll use. Okay. So what do you want to do? Okay, so let me kind of try to do it more. I'll see if this kind of looks okay, and I'll try to explain it then why more like algebraically how I want to think about this. Well, no, I actually like kind of trying to do it like from the beginning. Okay. So what you kind of want to do is kind of like do something close to this where I was breaking up, 6 into products, right? Like that kind of makes sense because you see when you got this to this step, you could see like secretly there was like a multiplication happening here. It's just the multiplication that I want is slightly different one that the one I wrote here. But it like, we did find some useful information just by breaking up 6 into products. So what I will think about is kind of like um, thinking of 6, for example, as 2 times 3. Okay, so 6 is 2 times 3, fine. What is kind of special in this particular case is that, these two numbers, if you add them together, 2 plus 3, you get 5 here. Okay, so there is like, it wasn't not super obvious, but there is a relation between 5 and 6, which is not clear, maybe not so straightforward, but if you write 6 as 2 times 3, and then you add those factors, which is how they're called, like, or divisors of 6, 2 and 3 add up to 5. Okay, so how can you kind of use that to your advantage? And I'll kind of give you like a more like general method in a moment. But what that means is that you should think about 5x as 2x plus 3x. I'll kind of let me put some colors in here. Kind of like the first step that I'm doing is writing 6 as 2 times 3. Okay. And then I'll write 5x as 2x plus 3x. So let me write just one more step with a like exactly the same as before. And now it is kind of close to what we had earlier, where we had like the sum of 4 terms. That's what I was trying to get at secretly. And what you can do here is start similar to what I was doing there, where I would factor out an x. So if you factor out an x, you get, for the first term, you get x plus 2. Okay. And then what is in common here? Like 3 is common. It appears in both terms of like the remaining terms. So I'll put 3 here as the common factor.
What happens to the remaining two? Or is it already included? Oh, it's already included.
You know, these two, oh, sorry, like, where's, no, these two is here, right?
Yeah.
Thanks. Is that making sense so far?
So are we just grouping up,
Mhm.
we're grouping them up and then we're factoring up the answers?
Well, in this case, I'll kind of say more concretely in a moment, but we're grouping them up in pairs. So for the first one, what I did take out an x, but for the last two, I didn't take out the x, because like if you look at the last two, x isn't common in the last two terms, right? X is only present in the third term, it's not on the fourth term. So I couldn't factor out the x for the last two because there's only an common x, like, you know, the x is only common for the first two. The thing is, like, I kind of want to, you know, do like from 4 to 2 and 10 to 2, like to like a product of two quantities similar to what I was doing here. So that's why I didn't like, you know, that's why I didn't group them like 3 and 1. I did it like 2, 2, basically. But what happens next, like, you know, is that now what you have in common is x plus 2. So x plus 2 is a common term. So that's the one that you would factor out. Okay, and then you get x plus 3 as the remainder stuff. And so now the cool thing once you get to this point is that you have the product of the numbers being equal to 0. So like the product of the numbers can only be 0 when at least one of the numbers is 0. So the product of two numbers can be 0, or so the product of two numbers when so you end up with x plus 2 has to be 0 or x plus 3 has to be 0. So x plus 2 equals 0. Or x plus 3 equals 0. So that gives you that x should be -2. So x equals -2 or x equals -3. Which, by the way, is what we kind of found also by trial and error a bit earlier, because we, you know, like that's where like one of the possibilities that did come up were present. But the idea, you know, maybe it doesn't look so clear why this one will be better. But the idea is that this one will make it better. You'll see in a second once I kind of write it down more explicitly, because it will always work in a way that is more straightforward than before. Yes.
But when we're setting it up, because
Mhm.
isn't it like the equation like A plus B equals C, is it, or like I think it's during the school year where it's like, what times what equals C and adds up to B?
Right,
Or
that-
what times what equal, or what times what equals B and adds up to C?
Uh,
How you both define it.
correct. So the idea will be to break up, that's what I'm about to write. Like the idea will be to break up the one that doesn't have an x into a product, in such a way that the factors add up to the one.
Because it's AX and BX, or is it
Uh,
AX?
Well, the way in which, usually, if you're thinking about the A's and B's, like the way in which usually this is written as is something like this.
Yeah, that's what I was saying.
For now, I'm doing the case where like the A is actually one, because it just makes it a little bit easier to explain. And then I'll do the case when there's an A, here. But yeah, like the trick will be to kind of write the last coefficient, or what is called like the constant term, into a product of numbers where the product adds, if you add up the factors, which is how they're called, they add up to the B, and then this would always work.
So when it's x to the second, that coefficient is one. And then when it's AX, it's the coefficient.
Right, when it's AX, like the AX squared, then the coefficient would be just be A, but like the thing is like, you only need to kind of master the case where the coefficient is one, because then you can always do a trick, which I'll explain in a second, to make the coefficient one. So really only the coefficient one is the one that matters, and it is like a little, it's easier to learn that first, like in that way. So but like what I'm trying to say is that, yeah, the key here is which is, there is always a little bit of trial and error to this method, which is kind of it's a game of how do you break up this into a product of two things so that those individual components add up to the one in the middle, in terms of the number. So basically, let me try to explain what the strategy is. I'll kind of, and then I'll do some more examples, to show you how this works out. So what is this strategy? So what is the main idea? So you're trying to solve, x squared plus bx plus b equals 0. So that is the equation that you're trying to solve. And the goal, so here's what you're trying to do. You're trying to decompose C as a product of two numbers which add up to B. So as a product of two numbers. So I want to write C as a product of two numbers. So for example, in this equation, in this example, C was 6, and I wanted to write it as 2 times 3. In this case, that ended up working. With the property that those two numbers add up to B. So what I want is B to be able to be written in the sum of D1 plus D2. Because what happens if you do this? So what is the point of like what occurs if you succeed and are able to do that? Well, so what occurs is that when you have something like this, B is like the sum of, like, if you succeed in doing this, then B becomes the sum of these two numbers, D1 and D2. Here D1 and D2 stand for divisor. So these are like kind of numbers that divide, or like factors of B. D1 plus D2. And then C is D1 times D2. Okay. And then this is x squared plus d1x plus d2x plus d1, d2. And so there's an x here, so you do exactly the same thing that I was doing a bit earlier, or you factor out the x for the first one, so you get x plus d1. And then you factor out the d2 for the second one. So you get x plus d1. Okay. So, and then you get an x plus d1 common term, which you can factor out. And this one gives you x plus d2. So my point is that if you, sorry, I should use it. If you're able to do this, the idea of doing this is that if you find those two numbers, d1 and d2, then you can always rewrite this expression as a product of these two linear factors. So if you, so let me just to summarize, what that ends up doing is like, that's kind of like the justification. Then you can write, rewrite x squared plus bx plus c as x plus d1 times x plus d2. Okay. So I'm going to do it for a few more examples of the using how this works out. But that is the key of like factorization for like, like the factorization that we're going to do today. It's kind of like a bit of trial and error, but the goal, like the objective is to find like how to decompose the constant term, like the one that is not next to an x or an x squared, in terms of two numbers that multiply to the constant term, but add up to the one in the middle, basically. And so let me right keep this here, but then like the important idea. So let me do it for a few examples to get this more to clear it up. So here's the first one. I mean, after a while, you kind of don't have to you don't have to do all the steps that I'm about to do, but for now, I'm kind of going to show you all the things that you could consider doing. Okay. So when you have something like that, again, the goal is to look at the constant term. The constant term in this case is 48. So how do you break 48 into a product of two numbers? So you can try all the possibilities like that comes to mind. So here are a few possibilities that comes to mind. What is 48? 48 is 1 times 48. That's fair. Like so that's 1 times 48. What is 48? That's also 2 times 24. That also works like as a decomposition. What is 48? That is also 3 times 16, right? 48 is also 4 times 12. 48 is 6 times 8, right? And if you keep going, right, if you increase like the first coefficient, like the first term, then you would get like, for example, to 8 times 6, and then you're going backwards, if that makes sense. So that, at least in terms of like breaking it up into products of like integers or whole numbers, that is more or less the best you could do. Like these are like the decompositions in terms of products, if that makes sense. And then you ask, okay, those are like my candidates, all these are candidates, and you ask, what happens if I add up these numbers, right? So you add up these numbers, you get 1 plus 48, which is 49, 2 plus 24, right, which is 26. Then you get 3 plus 16, which is 19, right? 4 plus 12, which is 16, right? And then 6 plus 8, which is 14, right? So of all those possibilities, it was, in this particular case, it was the last one, right? It is the last one that matches the coefficients in the middle, right? So what that means is that this, well, so far so good, everyone, up with me up to this point. So again, if you break it into possible products, these are all the possible products I could think of, and then you just ask of this break, like, ways to factor it out, which of the factors add up to the one in the middle. So only the last one adds up to the one in the middle. So I keep that one and I ignore the others. So like, once you have done this like a couple of times, you kind of like don't think, you kind of ignore the first few cases, like you don't even think about them, but it's kind of like good to lay it out explicitly so that you see like the kind of like the process like of elimination. So you say, okay, then according to the property, this just breaks into x plus 6 times x plus 8. So it just breaks into a product of two linear factors where the summand is like the individual components that appear. And why is that useful? Again, because why is it useful? Why does this matter? Because if I wanted to solve x squared plus 14x plus 48, for example, equals 0, thanks to this factorization, this would be the same as x plus 6 times x plus 8 equals 0. And once you know that the product of two numbers equals 0, one has to be 0. So x plus 3 has to be 0, or x plus 8 has to be 0. So x has to be -6, or x has to be -8. So the point of doing this factorization is that it makes your life very easy once you need to solve quadratic equations, which is one of the main objectives of the course, because quadratic equations or quadratic expressions appear everywhere in mathematics and applications and other places.
Wait, how would you set the equation of after you find the two numbers? So is it x to the second plus,
Oh, you mean this one?
yeah, like if I wanted to like put it in that equation right there that you first gave us, for
Mhm.
x to the second plus like
So,
6x plus 8x times 6 times 8. So like,
oh, how do I get from here to here? You mean? Or?
yeah, like how do I break down 14x and then the 48 into the?
Oh, no, like so the idea is that that's why we did all this process. Like the idea is you break the 48 because that was like the one without x into the product of numbers, right? With the extra property that those two numbers add up to the coefficient in the middle. Once you have found that pair, in this case the pair was 6 and 8, right? Because 6 times 8 is 48 and 6 plus 8 is 14. Then the breaking is kind of like always going to be the same. It's always going to be x plus one of the factors times x plus the second factor. There's no there's no change in that sense. So it's always you know x plus one factor times x plus the other plus the second factor, basically. Let me do it in another example, like just to see if this because this one is a little bit more interesting. So let me erase here, like kind of just to give it a chance to come. Today, that's like the only thing we'll do is factorize. Like, okay, so it's exactly the same type of process, right? Um, but there's something that has to be fixed in this case, you'll see what happens. So I take the coefficient, which is like the term which is constant, or the constant term, which has no x, so 55, right? And so what can I say? How can I break this 55 into products? Like I would say, well, 55 is 1 times 55, right? Or 55 is what? 5 times 11, right? And it could also be 11 times 5, but that kind of brings you back to where you started, right? So these are like the two possible ways to break 55 as a product of two numbers. Now, the other quality that this should have is that the numbers should add up to the one in the middle. What is the problem here? Like if you add up the numbers, right? Like you get 1 plus 55, which is 56, and then you get 5 plus 11, which is 16, right? None of these have like a chance to get to the middle one. Yes. Oh.
You have to make them.
Yeah, right. So exactly, that's a fix, right? Like you can also write it as -1 times -55 minus gives you a plus, right? Or -5 times -11. Okay, and that kind of does fix the negative coefficient issue. And now you have -1 plus -55, right? Which gives you -56, or -5 plus -11, which gives you -16. Oh, but -16 is right here. Okay.
So do you have to turn both of them negative, like?
Oh, right, because say if you had only turned one of them negative, right? Then positive with negative, I mean, you can try it out, but in this case, if you had tried like I mean, like the thing is like, sorry, they have to have, if you do one and -55, then they multiply to -55, not to 55, because like, a positive number, if you break it as a product, they both like, positive is positive, negative is positive, but if they have opposite signs, they give you something negative.
Yeah, but I was asking if like I thought that for the 55 and then like the 16, both of them negative. In the equation that was right.
Oh, the thing is like you mean like here?
Yeah, so when I break it down, what I have to do,
Oh, but you mean like it's a product of
Yeah.
two, okay, it's just with, so first, just to say, which is the one that works, this is the one that works, right? Because like, it's the one that matches like the -16. You just copy them with as they come, so like, it would be x plus -5 times x plus -11, which looks ugly, so you just write it as x minus 5 times x minus 11. But you see, like, it's just like the numbers as they appear here. You don't have to touch them or like fix them or anything.
I think your question is that, if that x, the part of 2 minus 16x minus 55, what if you change the?
Oh, that's what,
Yeah.
okay, sorry, okay, so let's work it out. I had like something like this. Okay, so now, like I would have to do, then they do need to have like get opposite sides, right? So one option would have been something like 1 times -55, right? Or -1 times 55, right? That's another possibility now, because now you have to decide where you want to put the minus, so kind of you double the options. But also you could have had -5 times 11, right? That would also be a third game, and also 5 times -11, right? So let's see if any of these work, because it's not super obvious whether this would work or not, right? So now if you add them together, you get +1 plus -55, right? Which is -54, -1 plus 55, which is 54, right? Then -5 plus 11, which is what is it, 6, and then 5 plus -11, right? Which is -6. Is that making sense so far so good? And so what happens here is that actually none of these add up to what we would have needed, right? Which is -16.
So that would be a no solution, or how would you say?
Oh, no. So actually, we will learn another, a more general method to solve these types of situations. So like our method does not work really well for this. There will be a more general case, which is called the quadratic equation, like the solution in terms of like involves square roots and other things. So this is kind of like an indication that the solutions will involve like things like involving square roots and radicals. So it's just like this kind of like, there's no guarantee that this 100% works. Obviously, if I want you to do, like, if I give you a problem with sort, it's because it will work, but I'm just saying like, for this particular case, just changing the sign messes everything up, and the strategy is no longer feasible, if that makes sense. So here, like, the factorization wouldn't be kind of very convenient. That doesn't really work well. So it is very sensitive to the signs and everything, like, it's probably good to do an example where it doesn't work to see what happens. But yeah, like, I don't think, Wednesday, but probably by Thursday, we may have enough stuff, information, so I can give you like what to do in this case, and this is called the quadratic, formula. But it's a little bit more tricky, and this does cover a lot of, useful cases which appear in practice, so it's kind of like useful to know how to do this, because it does appear often, like where this just works like on the get-go, and you don't have to do like this quadratic formula. So for a second, let me continuing in this same stuff, just to do two more examples. I'll do one more with the coefficient equal to 1, and then I'll do one with where the coefficient is not 1. Okay, so here is the same as what we were discussing, like I have the number which is -4, that's the one I have to break up into products, but since it is negative, I need the products to have opposite signs. So I could do, like, for example, 1 times -4. I could also do -1 times 4, right? I could also do 2 times -2, that would also work, okay? So, and like, like putting the minus in the other one doesn't really make a difference because it's 2 and 2. So those are the only generally 3 possibilities. And here, when you add them, you get 1 plus -4, which is -3, then -1 plus 4, which is 3, and then 2 plus -2, which is 0, right? So we wanted the one with 3, right? So that's the one. So the numbers that I have to use are -1 and 4. These are the important numbers. So this is the same as x plus -1 times x plus 4. And again, this is kind of ugly, so you just in bracket write it as x minus 1 times x plus 4. That makes sense. Okay, then just to do the last one that I wanted to do before giving you a chance to try some of them out after doing the quiz. Let's do one where the coefficient is not 1 in front of x, right? Which is also an important case. So let's do this for nine. Okay. So this is like, again, like an interesting one because, what's interesting about this one is that like this coefficient is no longer one in front of x one. So what you can do first, it's like a useful trick to kind of like artificially make this a coefficient of one, which is the following. We'll so I want to kind of factor out these two. That's kind of my goal. The problem is these factors don't have a two anywhere, so you can kind of always put it by force by multiplying and dividing by two. Because 2/2 is one, so like I'm not doing anything if you multiply by one, if that makes sense. So 2/2 is one, 2/2 is one. So you can always multiply, like in that sense, you can always like multiply by two, but like the price you pay is to divide by two, so that like the expression remains unaffected. But if you do that, what is the cool thing about doing that? That now there's a two everywhere that you can factor out. And then 3 times 1/2.
Is it possible to just like take out the like factor out the two and then do the whole thing and multiply?
Well,
Get by two.
Well, yeah, that's exactly, like here I factor out the two basically. So that is essentially what I'm doing. It's just that what I was saying is that to factor out the two, you kind of have to like, I mean, it kind of looks weird to factor out the two here because there's no two explicitly in the middle term or the last term. So, but you can kind of like make them show up by multiplying and dividing by two in the middle and the last one. So like it just becomes, when you factor out the two, essentially what you have to keep in mind is that you, instead of having three, you have to have three halves because now you have half of like the amount that you had before. And instead of having nine, you have nine halves. So you can go from this step to this step, if that makes sense. If not, you can always kind of do this trick of multiplying and dividing by two.
Right,
Um,
so. Wouldn't it be easier to do the AC method on this?
In like, well,
2 times -9 and then.
right.
And then you try finding, what was it? The things that multiply to, whatever AC is multiplied to. A and C is multiplied to, and that addition to that, this.
Right. I know, yes, it's just that sounds like a little bit harder to, I mean, yes, it is equivalent to what I'm doing, but it just, you have to like, kind of remember more things because like, yeah, you want to kind of like break it like into. Yeah, like, like something like, so you want something like this, right, or, but now these two numbers need to give you two, right? These two numbers need to give you -9. And they're kind of like this one with this one and this one with this one have to give you -3, right? Or which is essentially what I'm doing. This is what I'm doing, but what you have to keep in mind if you do it that way is more things to, there are kind of more conditions to keep in mind because they're like, now you have to break these two into products, right? Then they add up in these weird ways to the one in the middle. So it's not that it doesn't work. It is the same as it is the same as this basically. So, but it's just like the thing is like when it's in one, it's nicer to memorize. It's easier to remember what to do with the one because it's only this term that you care about to write it as a product, and then those two factors add up to the one in the middle. If you kind of do it with the two in front directly, then yeah, like there's like these other extra conditions, but it is, I mean, both work, if you know what.
Could we change it then, like, if we were to multiply A by C, would it be x to the second minus 3x minus C,
let's see.
minus 18 to like factor out?
Oh, yeah, like, well, I mean, yes, like, that is essentially what, 2 times 9 here is like the 18, so yeah, it's like 18 half, yes, exactly, yeah.
And we can still keep the 3x as 3x.
Well, that is, well, to factor out the 2, you would have to write it as 6x over 2, but it's also like the same as,
Yeah,
I have here, basically. But sorry, did I answer your question? Like, so I'm not saying that, like, it does work, I'm just saying, like, I try to find like methods where you memorize the least amount of stuff, you know? And I feel like if you kind of try to do it this way, you have to memorize more stuff, like, you know, because it's like, okay, and then you have this times this gives you the 2, then this times this gives you the -9, and then you have like those mixed products that have to add up to the one in the middle. Which sounds less more confusing than I guess like always doing it with one, you know, because it's only like the last term factor and then like make sure that the numbers add up the way they're supposed to. But you'll see like ends up being the same basically. So. So for example. Yeah, so like you just have to look at -9 halves. Okay, and then you just break it into products, so like, you know, I'll kind of like, again, like you kind of end up getting used to these in practice. There are not that many ones that you have to look at. Okay, so those are all the possible ways of breaking it up. And then you kind of like when you add up the coefficients, you get -1 plus 9 halves. This one gives you 7 halves, and 9 halves minus 1. This one also gives you. Oh, sorry, I kind of like these two are the same. Sorry, I made a typo. So this one should have been what like this. Like what did I do here? Like I made a. I think I meant something different here. So that this one gives you -7 halves. So that's what I should have done. And I mean, like you'll see this 3 halves plus 3. Oh, sorry. And then why is there one? Like it should have been -3. And then minus 3 halves plus 3 gives me 3 halves. So this is like this is the one that's going to work out. Second, because it's the one that has 3 halves. So you don't have to finish the other ones once you have done them, but you know, I'll do that. Also, sorry, this is more. 17, 2. So yeah, I'm just I mean, because like it's a little bit with fractions, so you just have to kind of double check and a bit more carefully. But 3 halves and -3 are the ones that work. And we get 2 times x plus 3 halves times x minus 3. And then you can multiply the 2 back in, and then you get 2x plus 3. But when you multiply, just multiplying one of the factors. You know, you cannot multiply both of the factors, like it only goes into one. So this is fine, this is fine. You could also have multiplied it in the other one, although it looks a little bit weird because you kind of try to avoid fractions in general, but it's also fine to write it like that. So all those 3 are options of how to write it out. But the point is that, you know, I'm trying to kind of give you a method that to say that even if the coefficient is not 1, you can always reduce it back to the 1 coefficient case. Or alternatively, yeah, you could use like this other decomposition, but just requires memorizing a bit more, which I'm trying to avoid. Kind of like memorizing it, and try to make you memorize as little stuff as possible, basically. And it's kind of like in practice, it's very useful. It's see like it is like a useful idea to understand, like to keep in mind that, oh yeah, when you want to solve something like this, once you understand how to solve it, when the coefficient is one, you kind of understood everything, because everything else is just like a special case. Okay. Okay, so let's do the quiz, and after that, I'll just give you some problems for you to factor out on your own to make sure like this is like it's enough.